Okay, hello everyone. Oops. Okay, here we go. So we are going to continuing on our whole workflow through machine learning, right? We're trying to see, we just saw, so let's reorient. We just saw a few different kind of model classes, right? We were able to frame the abstract regression classification kind of problems as geometrical ones, where we need to draw curves or draw boundaries somehow. So we see how it works a little bit in the abstract. Right now, I'm highlighting a bunch of issues that happen in practice, right? So it's one thing to be able to draw curves in some sort of abstract space. It's another thing to work with a data set which might have all sorts of strange anomalies or characteristics which make it a little bit tricky to work with. Right? There are also going to be a whole bunch of tricks related to featurization, which can take a model or kind of an actual practical modeling problem from being not very effective to being much more effective. Right, so we're going to discuss some of these points in this next part. And yeah, I think we can get into that. We'll spend the rest of the session, after we discuss featurization and after we discuss preprocessing, we'll spend the rest of the session discussing model evaluation. Maybe if we have some time, visualization, but I think evaluation is an important enough topic that we should spend some time on it. Okay. And again, if at any point you have a question, just send a message in the chat. I'll be checking it. Yeah, I think it's always a little bit tricky to do it virtually, but be brave. Right? In a way, it can actually be easier to have questions just as they come in a chat, and then we can address all of them too. Okay. So we had mentioned a little bit outliers as being a potential preprocessing issue. Another one of the issues I want to highlight is differences in the ranges, right? So you can imagine this as being a kind of, you would really like the methods that we use to be kind of invariant to the units that we use to measure them. And like what I mean is like, maybe the predictor of for some problem is like the length of the tree branch in centimeters. It's kind of bad that if you reframe it from being measured in centimeters to being measured in millimeters, it's the same measurement, right? It's the same data. But then if you just change the units like that, that can actually change the model prediction. It doesn't change all the models. Like tree models are still okay. Linear regression still okay. But a lot of other methods are very sensitive to this sort of changing in units, right? So sparse linear regression are kind of maybe the most sensitive to this. It turns out that deep learning is also very sensitive to this, right? If you had different predictors that are very different scale, right, it makes a difference. So that's like what this picture is showing is like variable 1 it has a certain range. Variable 2, maybe just by the fact that it's being measured in millimeters instead of centimeters, it seems really long, right? But that's just an artifact. That has nothing really to do with the truth, right? So what you want to really do is you kind of want to rescale it so that they're a little bit closer, kind of more comparable ranges. So this is why when you hear people talk about standardization, that is kind of what this problem is. It's computing the standard deviation for each of the features and the mean for each of the features, and then kind of squashing them all so that they all have the same mean, they all have the same standard deviation. Right? You can think of it as like if the histogram for each feature at the beginning, they have these very different means, there's these very different standard deviations. Right? These are all the different features. It's like d equals 1, 2, 3, 4. After standardization, the histogram of each of the features, they're going to be all kind of more lined up. You might actually still have some changes in the shape, right? But then at least the mean standard deviations will be about the same. Okay, so that is this one potential issue. Check the scales of all your units or of all your features. Second issue, really common. We already saw it in the penguins data set, right? But it's missing values. So you know, geometrically, it's kind of tricky to think about what is the geometrical interpretation of a missing value. It's like our sensor broke down, or maybe someone didn't reply to a certain survey question, right? Also, these sort of things happen a lot in real data. Models don't automatically have a way of dealing with them. Either have to throw it out or have to do some sort of imputation. And we'll talk about what imputation is in a minute. But before we're talking about how you fix missing values, let's see how you can try to understand whether it exists. And so here's a plot that I really like for if you want to see how much missingness there is. This comes from the NAAMII package in R, but I'm sure you could try making this in any language you want. What this plot is showing, each row is a different observation, and here are the different features in your data set. The black columns, these are the missing values. So this is from some sort of meteorological sensor device. I think each one of these is a different day. So the wind sensor, temperature sensor, these are always working. But sometimes the solar sensor breaks. So like 5% of the cases, it breaks. Ozone sensor seems to be breaking pretty frequently, 24%. And what's kind of neat about this plot is it's showing not just the frequency at which it breaks, but it shows you the pattern of breaking. It shows that like solar, it broke in a few kind of consecutive groups. And ozone had like these 3 really big failures, right? It had this one, this one, this one, these few big failures, and then a few scattered failures all throughout the year. You can also start saying, I think these were in the summer, so it tends to break more in the summer and not as much in the winter. Right? But just from this one plot, you can start seeing not just like how much missingness do you have, but where is it? Okay. So how to fix it? Okay, I think I mentioned easiest way to fix missing values. Replace the missing value by the median of all the observed ones. So what does that mean? So you can imagine we have some column. Stop using red. It's okay. So imagine that these entries of the column are missing. What you can do is, for all the observed ones, make the histogram for the observed ones, take the median from that histogram, and then just plug in that mean value for all the missing values. This is called median imputation. Okay. So that's one way of doing it. It's usually pretty easy because you can calculate the median of the observed values very quickly. But it's actually not the most sophisticated way of doing imputation. And the reason you can imagine based on this figure, right? The main idea is that you can try to exploit correlation across several different features to try to better fill in the missing ones for each feature. So imagine here V1 and V2, these are 2 different features. Feature 1, feature 2. The orange points, these are observed for both features. Right? But then the points along the side here, like these points are only observed in V1. They're not observed in V2. Right? And vice versa. For these are only observed for feature 2, not for feature 1. That's why I'm drawing them this. I just kind of make up a value for V1 for those observations, right? Now, if I tell you that like this was the value for V1, but I didn't observe the value for V2 for this observation. imputation would just try to find the median. I'm sorry, I think my internet just crashed for a second. Okay. Okay, sorry about that. Okay, so where were we? We were trying to figure out why you can do better than median imputation, right? So remember, median imputation is going to take each of these observations and it's going to impute the missing value with just the median of the V2s. So it's going to try to predict everybody here. It's going to move them all to the median value for V2, and that's going to be the new filled in values, the imputed values for V2 whenever it was missing. Right? But this is not a good strategy, right? A better strategy okay. But yeah, I think this is the main idea. So this is the main idea for, this is called multiple imputation, right? So rather than just predicting everybody in V2 along the median for V2, use information from the correlated other variables to fill in what would be a plausible value for V2 when it was missing. Fill it in along this diagonal. That's much better than always predicting the same median value for that missing feature. Okay, let's move on to the next pre-processing idea. Okay, so for categorical data, right? None of the pictures I've drawn really applied to categorical data, right? We were working with some sort of numerical predictor all along. So what we need to be able to do is we need to be able to convert any column, like this is like a canonical categorical column, right? It takes on two possible values, the apples or oranges. But then kind of our geometry, our linear algebra, anything that you're throwing into the computer, it's not going to know how to handle those strings of letters in any natural way. So what you have to do instead is you have to code it numerically. And how can you code it numerically? In this case, like you just define new columns, right? One for each of the levels of that categorical variable. And then whenever in the original data you had that level, you're just going to put a 1 there, right? And since this one's orange, we put a 1 here. This converts it into a numerical problem, right? So now I can have a feature, right? And then and this is like the apple feature, and I can actually explicitly write it as here there's zeros and here there's ones, right? And you can now like plot that against different response values. Okay. So that is another common problem with categorical data. So a few. One, you might have categorical variables which have many, many levels. This is surprisingly common, right? You do not want to try doing this sort of coding if you have 1,000 levels for some variable, right? What you can do instead, there's an idea called response coding. This is right here. What response coding would be like is imagine you had, say, kind of the election turnout for every city in a country, right? And there are going to be thousands of cities in this data set. It doesn't make sense to create 1,000 columns of zeros and ones that give the name of that city. That's just there are too few observations for each city. So it doesn't make sense. But what you can do instead is you can take the average of all the responses within that city, and you can use that as the predictor. Yeah, you take those 1,000 values, and then you take averages in each group, and you create a new column with the averages in each of those groups. Okay. Another kind of common situation is you might have a few categorical levels which are really, really common, and then kind of a whole bunch which only occur once or twice. Again, in this situation, doing this kind of straightforward coding doesn't make sense. What you can do instead is um, you can try just grouping everything that's very rare into like an other or a rare column, right? So sometimes this is called lumping. Yeah, once you've lumped all the rare categories, then you're down to a few columns of zeros and ones. You have like the most common categories are going to be coded here, and then everything else is going to be its own column of other. Okay. The main point I wanted to communicate here is you've probably heard, or like this K-hot encoding idea is very intuitive. It makes a lot of sense, but don't think that just because you can K-hot encoding or you can K-hot encode things, it means you don't have to think about categorical data anymore. And actually, there's a lot of subtlety when you have categorical predictors, and actually keeping track of how frequent they are, what their frequencies are, that can help you improve your model. You don't just want to blindly K-hot encode all the categorical data and pretend that everything is solved. Okay. Now for all the different kind of preprocessing that I've mentioned, so there's missing values, there's outliers, there's categorical data, right? And there's difference in scales. So how can you actually detect them? The plot that I recommend everyone make, all my students, I ask them to make this when they first get a data set, is I ask them to make a histogram, one for each feature in the data set, right? So, maybe I have, it could be even, 200 columns. It's like a big survey, and then you also have some demographic features, and then maybe environmental features. So you have a whole bunch of columns. Some of them are categorical, some of them are numerical. And then what I ask them to do is for all the numerical data, make a histogram. Maybe it looks like this, maybe it looks like this. And then for all the categorical data, make like a bar chart. Maybe you can just keep the raw levels, or you could sort the levels by their frequency. These are categories. Okay. It ends up being 200 plots maybe, but you'd be surprised by how quickly you can skim through a 200-page PDF just looking through a bunch of plots. Most of them are not going to be that interesting, right? They're going to be relatively similar characteristics across a bunch of columns, just because most of the time there's a lot of redundancy in the measurements that you get. But then sometimes you notice a structure that's like, oh, okay, we really need to rescale here. Or, oh, I noticed that in this group of columns, they tend to have a lot of outliers. Right? So just from making this set of plots, you can begin noticing potential issues, and it will make you kind of prepared to do the right pre-processing, rather than just like starting with a data set, throwing it into a model and hoping for the best. Okay, any questions about any of the pre-processing that we've done? Otherwise, I'm going to move into featurization. I'll wait a couple seconds in the chat. Okay, I'm going to move on to featurization. So what is featurization? Okay, so remember, I showed you a bunch of examples where I showed you a bunch of algorithms for linear regression, right? But then you might think like, why does linear regression get so much attention when I can think of so easily so many examples which are not linear, right? So here are two canonical examples. You have this quadratic curve, and then here is like a binary indicator curve. Definitely not linear. If you tried predicting, imagine this is y, like imagine predicting like y as a function of x. This is going to do really poorly, right? Like maybe you try predicting that line, and that's not very good. Or here, like maybe you try predicting that line, also not very good, right? And yet there's going to be a way to adapt linear regression so that it can do very well in both of these situations. And the main idea is you just introduce new features which are related to what we're observing here. So the example could be like, imagine the data actually are like this. So there's some noise in the response. This is why. Okay, so imagine there's some noise in the response. We want to be able to predict this. We just drew this blue line, and we know that the blue line is not that useful. It doesn't fit the data very well. Great. What we could do is we can introduce a new column. Okay, this didn't render proper, but I'll just draw it here. So imagine having, instead of the original x values, so the x values here is like -1 all the way to 1, and then it's like the x value for each of these points. So you have those original x values for all the data. It's like n samples. And then now, in addition to that x column, I'm going to introduce a new column, and I'm going to define it manually. And the new column is going to be zeros and ones. And I'm going to put a 0 if x is less than 0, and I'm going to put a 1 if x is larger than 1. Right? So mathematically, you would write that as an indicator function. Is x bigger than 0? Okay, it's like a question. If it's bigger than 0, you give it a 1, otherwise you give it a 0. Okay, so now, if you have these two features, so this is like x tilde, now you can actually perfectly predict these, or you can now make a prediction like this. Right. How is it that we're able to make this sort of prediction now? Well, think about what it means to do something like b times x tilde. Right. So for any value of x that's less than 0, it stays 0. Because for those entries, all the x tildes are 0 whenever x is less than 0. Right? So this part is like b times 0 is 0. Right? But then whenever x is larger than 0, and that's how we define the indicator function, whenever x is larger than 0, we put a 1. So whenever it's a 1, we have a b times 1, and then we get b. So now we're able to draw these lines where it's going to be 0 up until x equals 0. And then afterward, it's going to be the value b. And we can actually draw any of these values of b. They would all correspond to different kind of jump functions. And now it's up to linear regression, the optimization, to try to figure out which of those b's will fit the data well according to least squares. But the main idea to take away is like, introducing this new x tilde column was really, really valuable. We went from only being able to fit curves like the blue curve, right? Before we could only do things like this, right? Only blue curve, like that. But now we're allowed to do these sort of step functions where we have to be 0 up until 0, but afterward we can be anything we want. And that's just by the definition of x tilde. Okay, so this is the main idea for futurization. Even though we're doing a linear fit, we're doing a linear fit of something that's kind of inherently nonlinear. And then if you do linear mixtures of nonlinear things, you still end up with nonlinear things. Okay. Do you see how you might be able to do a similar trick for the first plot? So instead of having an indicator for x, you would do it like this. You would have the original x. That's what we always started off with, but the original x can only fit straight lines to this curve. In order to be able to fit this kind of curve shape, we'll introduce a new column that's just whatever the value was in that first column, but squared. Right? Now, what are the linear mixtures of x and x squared? Well, we can do like b1x, and then we can do b2 x squared. But now what is B1 and B2 actually defining here? It's kind of letting us do any quadratic function up to the intercept going through 0, right? So now that we've introduced both of these two columns and we're allowed to choose any B that we want, now we can fit, this quadratic function. That would be like having a really steep B2. We could fit this quadratic function. We could even choose negative values of B2, right? And we get a whole bunch of different quadratic functions. So if we observed data that were lying along this one quadratic function, we would have enough flexibility to be able to choose one of the quadratic functions that's going to go through that set of data. And all of this came just by being able to introduce this new column of x squareds, so that now if I do add those two features together with different B1 and B2, I can get any quadratic like this. It's the main idea for featurization. Okay, so I realize this example is relatively abstract, right? We're talking about, what does it really mean, these just quadratic and indicator sort of things. But it actually comes up in a lot of real applications too. So here's one to think about. And it's actually coming from a real application. So in the application, it was something like you have a bunch of lab tests for each patient, and you wanted to be able to determine whether kind of a year from now they will have been cured, or a year from now they're going to be kind of deteriorating condition. So the original data is actually just, it's like this big data frame where it has, this is T1, T2, T3, and you have all these time points for each patient. So each patient is this little curve. Right? And you have an assignment that's like recovered, did not recover, and then recovered again. Right? So you have a label associated with each of these little series. So you could, in theory, just fit a model. You could fit a fancy, like a tree model, you could do anything, just to try to predict from the raw series values to that response. But this is not that effective. A thing that works much better is to try featurizing the series. So I just gave you an example of really simple featurization, but you could imagine from these series, you could do much more complicated ones, right? So like this line here is looking at the overall trend, right? So you can define a new feature in your predictor matrix that's that overall trend. That's this slope. You could define a new feature also that's like, how much variation did they have in the time that I measured it, right? What was the range? And each of these properties might be predictive. Like slope is a very natural thing, right? Like if the slope is decreasing, then it might say something about the overall trend for that patient, right? And that could be very predictive. Even though the raw y values for each of the raw x values for each of those time points might not be that informative, the overall trend might be very informative, right? And the model has no way of knowing what the overall trend is unless you give it to it. So deep learning will be a little bit of an exception, but in most cases, you do need to kind of explicitly give features that might be predictive. Okay, so that's for time series kind of situation. What about for text, right? So text, you start off with these strings of words, but then you can convert it to document kind of word counts. So this is the bag of words model. So that's a very natural way to featurize a document. You've converted it into counts that never existed when you originally got the data. For images, you can try things like the average color. So it's a silly example, but imagine you have a whole bunch of pictures. Some of them are of the forest, some of them are of the beach. You don't even need any like really fancy image recognition thing. You could just take the average color across these images. And if you notice a lot of blue, then it might be a beach, or more likely to be a beach. If you notice a lot of green, it's probably a forest, right? So you can just take the average pixel value and turn that into a feature, and that's probably already relatively predictive. Okay. I'm showing you a picture here of a very fancy kind of oriented gradient feature of a flower. This is the sort of thing that people would be trying to define features to capture where the edges occurred in an image. They are actually very powerful, but then it turns out they're really tedious, and two, they don't always work universally, right? So learning your own features for every single problem, that does much better than trying to define a set of features in advance. And that's one of the reasons that why deep learning is so popular. It made this really complicated image featurization process almost automatic just by learning the relevant features. Okay, that is everything I have for featurization. Are there any questions? Okay. So let's do an exercise then. We can do a short one. So, so let's go to the second exercise, right? So in the second exercise, I'm asking, I'm showing a few different kind of situations where you might have to do modeling. And I'm asking you to construct a set of features that you can use to try to predict the response, right? So the thing I want you to try to do is don't just use the raw data that comes to you. Try to come up with things that you think might be associated with the response. And then, things that you think might be associated with the response, and write down what would that model look like. I have 3 here. Just pick one of the 3 that you like and spend 5 minutes working with a small team thinking about it. I remember in the last time we worked on an exercise, it looked like it locked a lot of people out because it's not used to having so many people join a Google Doc at once. If that happens to you, maybe just send me in Discord the text of your response and I'll just copy it in here. But hopefully it doesn't kick us out. I think if only one person per group go, it might be fun. Yeah, let's take 5 minutes. I'm also happy to answer questions on Discord or Zoom in the meantime. Okie doke. So let's get started again. Okay. So first, before getting into the next topic, I want to review a little bit what response coding was. I think we went through it really quickly, so it's worth explaining. Okay. So here's the idea. You have some feature, let's call it, this is like XD, and it has a whole bunch of categorical levels. So it could be like, like city 1, city 2, and then you have city 500, right? And you have a whole bunch of people from all of these different cities, right? In theory, you could have a predictor that said, or you could try encoding all 500 cities using this one hot encoding idea. Okay? So you could have like city 1 all the way to city 500, and you could have like ones saying, okay, this person came from this city, the next person came from the same city, and then the next person after that came from city 1, right? So you could imagine drawing something like that. But this is not a very good strategy, right? it introduces a lot of new features which are mostly constant. They're mostly all zero and only very rarely have ones. So it's very low efficiency. The idea in response coding instead is start with a new column. This is going to be our response coded column. Now think about everywhere you saw someone from city 1. So maybe this person's from city 1. These people are from city 1. This person's also from city 1. Right. Now, think about the y value. Think about the y value associated with all of those people. Okay. So each of them has some y value. And then you can take the average of all those y values, right? So you can have like a y bar city 1. Okay, I see question. And also, oh, sorry, I am not mentioning. Or do you see my good note? Or let me stop and start it. Okay, do you see the actual screen? And I also see there's a raised hand. You can speak whenever you're ready. Okay, thank you. Sorry about that. Yeah, this is what I was trying to draw. I was trying to draw, you have, so the most important thing here I'm trying to show is these. Right? So imagine these green circles. These are all the people who come from the first city. And then you look at the y value for everyone from that first city. That is what this y bar city 1 is. It's the average value of everyone from the first city. Now, in the new feature, the one that you're about to define, the response coded feature, look at the entry for wherever people from city 1 were, right? And then replace, like in that entry, put down y bar city 1. So y bar city 1 goes in all the entries where you had someone from city 1. And you can do the same for city 2 and for city 3, all the way to city 500. Why is this a good idea? So kind of one really nice thing here is that we have in a single featurized column information about all 500 cities. Right? That's not what we would have gotten if we were trying to do a K-hop encoding. The other kind of nice thing is that it kind of naturally finds the similarities across cities. So cities which have very similar values of y, they're going to get very similar response codings. And that's not something that you would have if you were just doing a K-hop encoding. Because K-hop encoding, it doesn't have any notion of city similarity. They're just all ones or zeros. Okay, so hopefully this was a little bit more kind of easy to follow response coding idea. I feel like it's one of these areas which is not talked about very much, but it does come in handy if you have categorical data with many levels. Okay. But that is all for featurization and preprocessing. Let's move to evaluation. Oops. Zoom is blocking. Okay. So let's talk about overfitting, bias variance, and cross-validation. So I told you earlier that everything was just about drawing curves through data, but actually that's not enough. Why not? Okay. So this seems like a silly example, but it's really serious. So imagine you have a whole bunch of, you have some feature X, you have all these samples. I tell you machine learning is just drawing curves through data, and then you draw this curve through the data set. Right? There's actually nothing I've said so far that says that this is a bad thing to do, right? I told you a whole bunch of models. I told you that you should try to use the past data to learn the relationship between the features and the response. But this looks a little bit silly. And why is it silly? Like intuitively, we feel like there is kind of a natural law, like a decreasing kind of curve here. Let me just check. Can no one hear me? I feel like I'm unmuted. Okay, yeah, maybe, I'm sorry, I don't know why. Okay, I'll continue then. Okay, yeah, so it seems at first like there should be some smooth curve and everything else we see is just noise. But how do we formalize this idea? Okay. So the main idea is to think this is just the training data. Suppose we had collected a few new examples from the same population. So imagine this is like me waiting for the bus, and then this is the number of people at the bus station, and this is 1 year of data. And then I collect data for another month, right? And I compare the new observations for that next month to the curve that I had drawn just interpolating from my first year of data, right? If I did that, so the gray points, these are new data. Right? And then the blue, these are the errors. So, okay, we have some error from the interpolating point that or the interpolating line that I drawn, and then these gray points. So far, nothing that crazy. But the thing that's really kind of amazing is imagine that we had just actually drawn a very simple, kind of the natural smooth curve, and draw the same gray points, the same new data. Now, if you compare the new data, the gray points to the green curve, they are much closer, right? So this is a little bit of a paradox, right? So, this data gets 0 training error. It perfectly interpolates all the training data, but it gets pretty high error on the new observations. Versus here, you get some training error. It's not just perfectly interpolating everything, but then the test error is relatively close to the training error, and it's definitely smaller than the test error here. So what has happened is we have overfit in this curve, and then by smoothing things out, we've actually improved the generalization. The generalization error is the length of these blue lines. So let's make that explicit. This has smaller generalization. Okay. So, okay, this is all regression, but just to say that the same thing can happen for classification. This is a super overfit decision boundary. It does really well on this training data, but imagine that, I might have gone here a red point, right? Then you would have wished that it had been a little bit smoother, right? So these weird curvy things, it actually might not ever reoccur in future data. So you're actually probably much better off having a smoother decision boundary like this. So this is called overfitting. This is very dangerous because it can lead to a kind of over-optimism. Right? If you are only evaluating the model on the training data set, and it seems like you're getting really great performance on the training data set, then you kind of go around telling everyone, you tell the manager, like, I've solved the problem, we can use it in the real world, it's fantastic. And then you apply it on new data, It's coming in from like new customers or new sensors or from wherever, and then it does very, very poorly. Like, that's not good. That is like, that's how you get fired, right? But that's exactly what could happen if you evaluated the data on the training set. So you overfit. Okay. So how can we avoid overfitting? There's something here around you want to choose the right level of complexity. Too complicated, bad. You would overfit, you interpolate the data. Not complicated enough, then you can't actually fit real structure, right? Like if I had made it a straight line, then I wouldn't be fitting the real structure here. I would be underfitting. Right? So I somehow need to strike a balance between overfitting and underfitting. Okay. So how are you going to strike that balance? You need to have some way informed from the data that we do have. So kind of the main idea is to do this sort of train and test split, or this is like the first idea. This is what it is. So this is all the data that we have available. Right. We just randomly select entries or randomly select rows to be training rows, and then the remaining fraction we make testing rows. On just the training samples, we fit models with different complexity, right? So what this picture is, the purple are the training samples, the kind of pinkish, they're test samples. When I fit these curves, I only look at the purple points. Right, so notice the complicated model is interpolating the purple points, but it's kind of ignoring the pink points. That's because when I'm training these models, like I can only look at the training samples. I can't look at the test samples at all. Okay, so I use the purple points to fit models. I have one really complicated orange model and I have one relatively simple green model. And then using the test samples, this fraction that you held out that you didn't use for training, you use this to evaluate the relative error of the different models. And like in this example, what you can see is that the orange actually has higher error on the pink points than the green. So it's the same phenomenon as before. But this time, we're actually able to evaluate it on data that we have. And the key insight is that just don't train on all the data, reserve some amount of it for doing this sort of evaluating kind of introspective stuff. Okay, so that's the one main idea to avoid overfitting. There's a second idea. Kind of, you might argue that splitting it, train and test like one split like this is pretty arbitrary, right? Why did these rows end up in training and not in test? It's all totally random, right? If you had had a different split, maybe you would have chosen a different complexity, right? It's very dependent on this kind of random thing. So a thing you can think is like, well, maybe I can just randomly select training and test many times. And then if I have many times and I still notice I always want to pick a certain complexity, that's pretty good evidence for choosing a certain complexity. But then if you just randomly select them, that's not so great either, because you might end up with very correlated training sets just because by chance you get a lot of overlap. So an even better thing to do is to split the data into explicitly different groups and then always hold out one group at a time so that you kind of decorrelate the different training sets as much as you can. That is what cross-validation does. So what has happened here is I took the overall data that I have, and then I've split it into thirds, or like nearly thirds. And then in the first cross-validation fold, I train on all the purple and I evaluate on this pink. Then I train on this like first third and last third, and I evaluate on the middle, and then I can do it out here too. The number of folds in cross-validation, so here K is 3, but then you could choose however many, right? You could choose 2-fold, you could choose 100-fold if you have enough data. And then each time you can compare your models, right? So it's the same kind of evaluation on the holdout set for the 2 models from before. And here is on each of the 3 folds, my simple model is doing relatively well, but my complex model is doing relatively poorly. So this is telling me I should choose my simple model. Right? Simple models are actually doing better than my complicated. Okay. You can imagine there might be a model like this, which is too simple. Right? It could be maybe you have some like straight line that's going through a curve. It's also going to get a lot of error. So there's usually some sort of sweet spot where it's like, here's too complicated. And then here's too simple. And then here's ideal. Okay. So some conceptual high-level points. Okay. Yeah, maybe I think that the most important is that I've told you that you should just randomly leave out data, right? You should like randomly split into train and test. In practice, there might be things that are issues. There might be problems with that. The main reason is because you might actually have dependence between your observations, and randomly splitting them doesn't respect that dependence. Like an example, like that's pretty abstract idea, right? An example could be, imagine you were trying to forecast the stock market, right? So I observe a whole big stock market kind of thing. If you were just randomly holding out observations, right? So like if I just randomly held out these time points, then it's like I'm observing the series like this, right? It's not too surprising that you can do a lot better here than if I had split the data so that everything up to a certain time is used for training and everything after is used for test. Right? The reason is that I know more about these gaps because I have data from the future. In real life, in the actual application that you care about, you don't have access to the future. So you should only be able to use observations from the past to make prediction at the current step. You shouldn't be allowed to use observations from the future to make prediction at the current step. So randomly leaving out days, that's not going to work here. It's going to make you over optimistic too. That's just one example. The same kind of thing happens in geographic data, right? So a lot of times, like maybe an internet company is trying to expand their market, right? So they've tried some new program in, tried it in some county, the neighboring county, and now they want to introduce it to a brand new county that's very far away, right? You could imagine just trying to randomly hold out observations, but a much better strategy would be to randomly hold out different counties, right? So in the past counties where you have observed data, try using a subset of the counties as training and evaluating on kind of holdout counties. Because that's going to represent the actual situation you're going to face when you actually try a new county. Yeah, it's just you want to make your cross-validation mechanism simulate the real world evaluation mechanism as closely as possible. Okay. So let's look at some code to do this. And you should be able to run this on the binder notebook as well. These are just the plots. Okay, so let's look at the penguins data set again. Before I was fitting it on the training set. It's not a good idea. Or I was evaluating it using all the samples. So shouldn't do that. What I'm using here is a function called train test split, also in scikit-learn. From that train test split, I'm going to take X and I'm going to end up with X train, X test, Y train, Y test. So it will automatically do that work of randomly assigning penguins into train and test. So I'm going to read it in and split it. Okay, I'm just double checking, making sure that the split proportions make sense. So I asked it for a test set size that's a quarter of the overall data set. So it's like the relative size of the pink rectangle is about a quarter of the height of the overall data set. And that looks about right here. So like 250 plus 80, like 80 divided by the total is about 25%. Okay. So now I fit the model, but there's a critical difference. Instead of fitting the model on all of X and all of Y, I'm only fitting it on X train and X and Y train. Only X train and Y train. Okay. So that's a key thing. I've also introduced a few new columns for Y hat on all the data, and also I've saved which rows we're training and which rows we're testing. This is just so that I can make the visualization that I'm about to make. This is not as important. The really important part is here. Know that when you fit, only fit it on the training. So remember, this is the model that got perfect training error before. If I plot the performance this time. Okay. So again, it gets perfect performance on training. But now, this testing, these are all the samples that have been in test. We make a few mistakes. So this penguin is predicted to be a chin-strap penguin. It's actually a Gen 2. I mean, I don't blame it for making that mistake because it looks very similar to some of the other chin-strap penguins as far as beak or bill length and bill depth are concerned. But then it is a mistake, right? And had we not used this explicit test set, we would not have realized that there are going to be some proportion of errors, even in this very fancy gradient boosting model. Right? Yeah, here's another error that we only see on the test and never on train. Okay, so that is just ordinary train test split. It does one split, it's random, but a bit arbitrary. Instead, we might want to do cross-validation. For cross-validation, a very handy function is this cross-val score function. So usually, if you were doing it by hand, you would have to like assign every row to a fold. You'd have to do a for loop to try to guess which rows to use. This removes all of that coding and just says, given a model, given the original data set, compute the performance across a few different cross-validation folds. And it does it all internally. So here I can get some accuracies on the holdout fold. Okay, and I see, so on one of the folds, it actually got perfect performance, but on all the other folds, yeah, in this fold, it did relatively poorly, actually. It only 90% accuracy, right? So we can start seeing kind of what is the typical generalization performance. Okay, so now it's back to the notes. That's all the code. Okay, there's this last relatively subtle idea, but I think it's worth making the connection to. So I had mapped it out as, you know, a one-dimensional thing. It's like a too complicated or a low or not complicated enough kind of phenomenon. But you can actually break it out into a few different components. So you can, this is like a kind of analysis, right? So instead of just saying over or under complicated, you can say, what is the source of error when it's overcomplicated, and what's the source of error when it's undercomplicated? And this is a cartoon, but these tend to be the two main kinds of errors you make. Imagine the thought experiment accompanying these pictures is this. It's like the true data fall along this purple line, right? But then there's noise. There's always going to be, like in the real data, there's going to be some noise around that purple line. And imagine simulating 100 different data sets that all have basically that same noise around the purple line structure. For each of these data sets, you can imagine fitting a very simple model, and you can imagine fitting a very complicated model. The very complicated model is going to try to interpolate all the observations from each of those data sets. Right? So maybe one of the data sets, it had observations lying like here, and then one of these curves is just exactly tracking those data. So it's overfit, but then the next time I simulate, since that pattern is actually just noise around the purple line, The next time I actually fit a different one of these curves, right? So even though on average, if you averaged all the orange lines, the average of all the orange lines is very close to the truth. Just because they're they either overestimate or underestimate by the same amounts each time. But then on any single data set, the curve is very far from the truth at many places. This is called a high variance fit, even though it's low bias on average. And then the other situation is, even though the data are all like each of the 100 simulation runs or however many simulation runs you do, even though they're all these noise around the curve, every single time this linear model is fitting almost the same line, right? So this model is very biased. Biased meaning it's has this whole region where even after averaging across 100 different models, all the models are wrong. There's this visible gap between where the average of the models are and where the truth is. But then from one run to the next, they're all very similar. So they're very low variance, even though there's high bias. And these tend to be the two different components of error. And then model complexity trades off between bias and variance. And usually you want to try to find an optimal bias and variance. Okay, let's zoom out again. Okay, a general, very practical tip, something like this, is I think it's often easier to start from a very complicated model and then trim it down and regularize it, rather than the other direction, right? I think the idea is overfit the data, because then you know that your model class is rich enough, right? It creates an upper bound for the possible performance. Once you have an overfit model, then you can try changing the amount of regularization for different parts of the curve so that it stabilizes it a little bit. But I think this is often easier than having a totally underfit model and then not being able to really do anything from just an under-rich set of features. Okay. Any questions about bias variance or model evaluation? I realize it's a pretty deep topic. I can probably spend a whole semester on this. But at least I hope you can see the high level practical takeaways. Oh, okay, I see a question. So how can we know that the data sets need data splitting? You almost should always split the data, right? Like if you care about evaluating performance before releasing it in the real world, you should do some sort of data splitting. Because otherwise you're just applying it to the real world blind without knowing at all how good it's going to be doing. Maybe the only exception I can think of is if the problem is simple enough that you can just look at the decision boundary explicitly, or if you can just evaluate the decision rule right away manually, then it might be okay. Maybe you might be able to look at the coefficients from the linear model and say like, oh yeah, that makes practical sense. Like that was kind of the rule I was already using internally without any mathematical model. If that's the case, then you can probably safely ignore data splitting. But then if you really are kind of wandering through a very wide space of models and you don't have a very clear sense of the model just from the coefficients or the fit, then it's helpful to do some sort of evaluation. Oh yeah, okay. So the low, or wait, what was it? The variance. Okay. So the idea in variance it's that um, it's that so okay, there's two parts to this question, right? So one is like, why is it high variance? And the other is, why is it low bias? I think the high variance one is very intuitive. It's when we're trying to interpolate the noise, then we have to make our function very wiggly, right? And that means the function is going to have to wander very far away from the truth, or from the true mean, this purple line, just because it's trying really hard to fit the noise. So it's going to have to wander way high away from the purple line before able to come back. So that explains why it's high variance. Right? So that's why it's not tightly, like ideally we would be kind of a whole bunch of lines that are all around the purple, and then we would have low bias and low variance, right? But that's almost like, unless you know the form of the model, that can be very hard to do. Right? So yeah, that explains the variance part. Why does it have low bias? So low bias, what it means is that if I averaged across 100 runs all those orange lines, and I try to figure out where the average of those orange lines is it close to the truth or not? So I'm not giving a real proof of why it's low bias. But then the kind of hand wavy argument is that you tend to overestimate and underestimate. So like when you are fitting the noise tends to be above the purple line or below the purple line with equal probability, because it's noise. If it had some systematic structure, then it wouldn't be noise, right? So the noise tends to be above or below with equal probability. And since I'm trying to interpolate the noise, the interpolation is also going to be above or below with equal probability. So on average, across all those different noisy runs, they will converge to around the truth, just because you average across many things that overestimate and many things that underestimate, and they cancel each other out. Any other questions? I want to give options to people. So we have 10 more minutes in the session. I don't think it really makes sense to try to do the fourth set of notes. Actually, to be honest, it's not as important as these set of notes. If you're curious, fourth set of notes is just different kinds of visualizations you might want to make after you fitted it. So yeah, it's more like optional. We can do either maybe another exercise, or if you want to do like a Q&A session, I'm happy to do that too. So maybe anyone with a strong preference, just send it in the chat or the Discord. Or if any of the chairs or organizers wanted to speak up. Oh. Yeah. Okay. I think we can do Q&A. I think like 5 minutes, not enough for a real exercise anyway. Okay. Okay, so there are a few questions coming in. So the first question was in the Discord about this orthogonality idea. And it's a major point, but then I can try to do more detail. So it came up when we were showing the classification boundaries. Okay. It was how I parameterized these boundaries. I said something about the vector B here is always orthogonal to the decision boundary. How to understand this? I guess it comes from thinking about the meaning of a function like this, right? So you have something like B transpose X, right? So the main thing to think about is like, where does this have, or like, what are the level lines? So like fix a value 10. Like where is B transpose X equal to 10, right? At first, this seems like a complicated thing to try to figure out, right? But then what you can try first thinking about is the easier one. Where is B transpose X equal to 0? Okay, so first of all, I have some vector B. The definition of perpendicularity in linear algebra is having an inner product equal to 0. So the set of X values where B transpose X is equal to 0 are exactly the lines that are perpendicular to B. So this is B, and this is B transpose X equal 0. Okay. Now we can think, like, so what about for this B transpose X thing equal 10 thing? Well, just imagine that you had one value of X where B transpose X was equal to 10. Like, let's call that X star. So suppose that B transpose X star is equal to 10. And just to be concrete, let's say this value, that is X star. You just happen to know that when you do this like B transpose X star, the inner product there, you know that one is 10, just miraculously. Right? But once you know that one, you can kind of add any point along this dotted line to that point, and it's still going to be 10. Why is it still going to be 10? Like, imagine that this, like this point here, this is like X tilde, right? So we know that B transpose X tilde is 0. So if I do like B transpose X star plus X tilde, that's still going to be 10. The reason it's still equal to 10 is because this contribution, B transpose X tilde, that is 0, because any point along the dotted line, those had to be 0 by the orthogonality point. Geometrically, what happens when I add X star and X tilde, right, I just kind of move in the same, I move in parallel to X tilde, starting from X star. Right? So it actually turns out you end up getting these parallel lines, and all of these will be equal to 10. And actually, that is why these decision, all the probabilities are going to be orthogonal to B in constant parallel lines. Okay. That's a little bit, that's much more math than we've done in the rest of the session, but I hope that helps the question. Feel free to follow up if you have any other questions about this. Okay, and I see some others. Besides the model you use, can data be biased? Can improper data sets have effects on overfitting or underfitting? Yeah, okay. Well, okay, we need to be precise about what we mean by the data set being biased, right? So I think there's like a colloquial sense that it can be biased in the sense of like it can lead to unfair predictions. And I think that's going to be the topic for a later session. But then I'm trying to think there's also like a more precise sense where the data itself, they're not representative of the population that you want to be able to do well on, right? So that can lead to a kind of poor generalization that you won't even be able to find using cross-validation, right? So you can imagine like you can imagine training all your samples on one very homogeneous population and then hoping to evaluate it on a totally different kind of population, right? No matter how much cross-validation you do on that first population, since it's so homogeneous, you'll never be able to evaluate the error on that kind of very different target population. So it's kind of this, you might actually end up underfitting the target population just because you don't have the right features, right? Or you might have become so overfit to the source data set that you can't do well on the target data set. But this is a very different question. I've assumed everywhere that the future samples are very similar to the samples that we started with. If you want to read more about this topic, it's called the problem of out-of-domain generalization. There's quite a bit of research on it now. Any other questions? Otherwise, I think we're about done. Also, if you ever have any questions about any of the materials that I've shared today, or want to learn more about any of these topics or the notes, feel free to reach out. I'm not sure whether, or my email is on my homepage. So if it's not already on the NAAMII website, you can always go to my homepage and find it. Yeah, thank you very much, everyone. I hope the rest of the sessions go very well.